All right, so there's some tests for special relativity, let's fall back on a thought experiment. So we got this idea of objects in motion are going to be experiencing some sort of relativistic effect. At least the outside observers are going to see it. And I've got this diagram on the board of, I'll just tell you what it is because it's hard to discern what it is otherwise. This green thing is an elevator. It's an elevator that's traveling at very high speed. So let's call it a relativistic elevator, okay? So this relativistic elevator is going very, very fast. In other words, it's an enclosed environment that has a high degree of acceleration. It's not just going fast, it's accelerating, it's going faster. And there's two different perspectives here. From the perspective that you guys are in, you're looking at, let's call this an electron beam. So there's an electron beam that was fired in through a little window in the side of the elevator. And this little window in the side of the elevator is big enough to allow a beam to come in through it. But within the elevator, it looks like it's just going to fly across the elevator. And if you and I were in this outside observer perspective, like think of ourselves like some sort of like a god that can see through walls or something like that, right? We would see this electron firing horizontally. It would just fire horizontally through space and we'd all be cool with that, right? And that actually doesn't seem very problematic because if the elevator wasn't there at all, that's what it would do, right? But then we think about how it would look if we were in the elevator. And that's what the bottom picture is. From the perspective of an elevator rider, or even from the perspective of the particle itself, wouldn't the floor be accelerating up towards you? From the perspective of the rider, you'd see the particle accelerating towards the floor. And again, on the surface, that doesn't seem like a problem. But if you were to have this object traveling at a speed really close to the speed of light, like let's just say 99.99999999999% of the speed of light, and the elevator was approaching speeds of 99.99999% of the speed of light, this actually does become quite problematic. I mean, think about it. Isn't there going to be like an X component to each one of those red dots? And if it's almost C, but then wouldn't there also be a Y component that's almost C? But then doesn't that mean that the tangential, Pythagorean theorem, angle velocity, isn't it going to be bigger than C? This is problematic. And so this guy here, this little problem, is something that really is kind of that gateway idea to general relativity. Special relativity is special because it's a non-accelerating scenario. All constant velocities, as long as you're going at a constant speed, special relativity. That's what's special about it. It's not special because it's hard. It's actually special because it's easy. It's the special case where you stay at a constant velocity. And really think about life. That really is a special case, right? Because it's not just elevators that accelerate. Doesn't it seem logical that anything with a gravity well gives rise to acceleration? And anything that has a gravity well is something with mass, which means that anytime you're in the presence of mass, general relativity will be at least a factor to some extent, right? So yeah, special relativity is all well and good, but we have to think about general relativity because you're always going to be hanging out around mass because you're mass, right? So this is an issue. So when we talk about special relativity being something that impacts the clock rates on satellites, yeah, but general relativity would be something as well, okay? And so like when we look at this guy here, people say, well, how do you keep that hypotenuse from exceeding C? And there's a weird effect that happens, and it's a real term, you can look it up, spaghettification. It turns out that since the speed can't exceed C, the space actually stretches to accommodate the fact that it would have to travel more distance so that it can't break the C barrier. And if you ever see these, we'll talk more about it when we get towards talking about black holes later on in the course. We'll talk about space-time warping. And I have a giant piece of blue spandex that some of you have seen. The giant piece of blue spandex is my space-time, fabric of space-time. and we're going to stretch the fabric of space-time and make gravity wells at some point. But this idea of space-time being elastic and space actually being a stretchy material that can be stretched by these acceleration zones that are created by gravity, this is going to mean that we have this spaghettification effect. And I think that this is maybe a hard one to conceptualize, that we need to stretch space in order to preserve speed. But it turns out that these acceleration effects that cause this bending kind of phenomenon to space-time are things that we've even observed. It turns out that this gravity well, can you imagine if I had a dent in a tabletop, like a big steel tabletop, and I try to roll a marble from the location of the star in this picture, and the dent is where the sun is? Can you imagine that the marble would follow the purple path, the pink path? Agree? It would kind of surf around the dent, if you like. Even if I rolled it straight initially, because the light shines out straight from that star, isotropic, all directions, right? But as that marble rolls across my steel tabletop, thinking of space like a two-dimensional surface, we know that the light would bend around the curve. It would surf around the curve. I had a pool table that was like this. It was a plywood pool table. It was a cheap one I got from my uncle. And I love playing pool. I have a nice stone-top pool table in my basement now, but my plywood pool table when I was a kid, it was warped. And I knew how I could ride the curves, and I knew how I could make that ball take the corners, in ways that a good pool table couldn't. We got light that comes from this star, and it rides the curve of that gravity well. It makes use of the acceleration. Now, the weird thing is, if you stand on Earth, like this woman here is, and you look up at the sky, and now this happens to be during an eclipse, so we can look right at the edge of the sun. And if you look at the sky, by the way, this is an experiment that's been done, okay? So it's not like this is just a thought experiment, but for us right now it kind of is, okay? But if you look at the sky with a telescope, which you really shouldn't look at the sun, but if you did, what you would see is, or what you could see, is a star just beside the sun. And from your perspective, it would look like there's a star just beside the sun. Now, if you're a good astronomer, and people have been great astronomers for centuries now, if you knew that star, and you'd know it if you were good, you'd know it by its let's just call it its stellar fingerprint, by its light spectrum that it makes, right? So you would know that that is a certain star. And if you had your astronomy down pat, you would know that star actually should be behind the sun right now. And the only way to accommodate for the fact that it should be behind the sun, but you're seeing it beside the sun, is this idea of what we call gravitational lensing. And gravitational lensing is this general relativistic effect that affects light, just like dents in a metal tabletop affect rolling marbles. It's got to follow around the curve in space-time. Why is the curve there in space-time? It's so that light can't go faster than the speed of light. That's all, because there's an acceleration zone around the star. I say that's all like it's an easy thing, but that's a complicated thought, right? Now, the other thing is, when I look at this, if we get extreme about this, and we do believe we have images of this now, think about it not just being a star. What if this was a black hole? And people get all excited about black holes. Could you look at a black hole, and could there be stars and galaxies and whatever behind the black hole? And if that was the case, and black holes have so much more of a lensing effect, bigger dent in the metal tabletop, if you like, wouldn't the light have to curve out even more around that? But then I think to myself, well, wait a minute. What's to keep the light, see this path here, curving to above the black hole? What about the light that travels along the path that I'm tracing right now? Couldn't it curve below the black hole? And what about, think three-dimensionally. And I one time had a student who was not sighted. He was a blind student. And he had an EA that worked with him. And his EA made models out of pipe cleaner that were the 3D representations of basically everything we did. And I thought oh my gosh, how is this guy going to do physics? He can't see. I was amazed. Those EAs, the assistants that work with people with different abilities, are so gifted. And what she did was she made a gravitational lensing diagram that had a ping pong ball where the sun was, where our black hole is, I should say, and it had a little bead where this star is, And it didn't just have a piece of pipe cleaner that went above the black hole. It also went below the black hole. It also went behind the black hole. And it also went in front of the black hole. Can you picture that in your brain right now? Like, isn't that wild? And then that was like the idea for this person, so that they could see that there would actually be a ring of light. If you were on Earth and you were looking towards a black hole and there was a galaxy in the background, can you imagine this lensing effect would make a smeared out ring of light around the black hole? That gravitational smeared ring would be evidence that it's a black hole, evidence of gravitational lensing. And you guys can do the Google on this one, see if there's evidence that if these images have been found. We've got images. It's a thing. I even had a friend that said he didn't believe in black holes and wouldn't believe in black holes until he saw the ring and saw images of the ring. And now he's a believer, because that was seeing was believing for him, right? But this is something that has been theorized well before the seeing, right? So this idea of gravitational lensing is a pretty neat idea, but it's also great evidence. Now, in the bottom right-hand corner, I got a picture of F equals GMM over R squared. And the reason I have that there is to remind me to say that this is not related to the force due to gravity acting on a mass. Say that again. This is not due to a force due to gravity acting on a mass. Light doesn't have mass. Photons don't have mass. They're not electrons. They're packets of energy that are massless. So this warping of space isn't gravity attracting an object and causing it to go in a curved path. It's an acceleration zone around a gravitational source that stretches space-time and forces things to take a different path. It's not attraction. Okay? Just like putting a dent in a tabletop, the dent itself isn't attraction, it's a warping. Okay? That causes the acceleration. So the force in the bottom right-hand corner there is not what causes this. And some people will say that contradicts Newton's laws, but it really doesn't contradict. It really just like is talking about it differently. It's talking about acceleration giving rise to general relativity, and not talking about force due to gravity causing attraction between two objects. Now, in a gravity well, I'm going to leave this one here for a minute. Can you guys take a minute? Just give this a quick run through, because I give it a read through. Because I feel like this is one of those where if I read it at you, oh, that's just awful. So if you're watching on video, pause, give it a read. People in class in real time, just give it a quick read. I'll leave it up there for a minute, okay? And I'll say this too. There's an equation here. This is not in the core grade 12 curriculum. You don't need to know this particular equation. The only reason I've got this up here is because I always have people ask me about general relativity and how it kind of would play out. So I wanted to steal a little bit of textbook information just to share it with you. We are only responsible for special relativity. I may ask you a little bit about that elevator. I might ask you a little bit about gravitational lensing, but I won't ask you anything to the depth of what's on the screen right now. Everybody get what I'm saying? But I do like that elevator and the idea of the gravitational lensing just as a way to have a simple explanatory, maybe sentence or paragraph type conversation. Can I keep on going? Yeah? All right. Now this one. Whew. Again, I'll leave it up for a minute, but there's a little bit more going on here than what maybe we want to put on a core physics test. We've got a vertical line that represents Earth's surface. We've got an origin that represents Earth's center. We've got a horizontal axis that talks about how far away we are from the Earth. And then we have a vertical axis that talks about how much time is gained by an object that's doing whatever the object is doing. Take a look at these curves. We've got a red curve, we've got a green curve, we've got a blue curve. Take a look at what's happening with GPS. because this is what a lot of us are concerned about, is how is the GPS going to be affected? And you can see that GPS is going to be existing along this vertical position. And you notice that there's going to be some net time gain based on the relativistic effects. That's our purple curve here. And that net time gain is going to be what the clocks on the GPS satellites have to accommodate for. Because timing is really important if you're trying to figure out position calculations for objects on the planet. Okay? And I got some connected videos we can talk about for why you would care about that. But the point is we got to care about relativity effects here. Let's talk momentum. Now, in classical physics, momentum, P, is just equal to mass times velocity. We are a little bit of the cart before the horse on this one, because we haven't talked about momentum just yet in this course. But it's an easy enough concept. Momentum is a vector value. It's not inertia. It's not energy. It's its own thing. And classical momentum is just P equals m times v. So we typically would write it as P equals m times v. And it's a measurement really of like the amount of, to me not very scientific, but the amount of oomph something has when it's traveling through space perhaps, right? And so what we say is that things that are traveling at really high speeds have a dilated oomph. And think about the extremes, because we love to look at the extremes. If something goes really, really fast, if this v value in the denominator ends up being a c, isn't the PO going to approach infinity? And so like in that sort of extreme way of thinking, what that tells us is the faster something goes, the more over-oomphed it's going to be, right? And so do we have evidence of this? Yes, particle accelerators show that if we get something up to a super high speed and those particles whack into a detector, they have way more oomph than if relativity wasn't a thing. Fair enough. Now the other thing is, if something has more oomph, doesn't it also mean that it effectively kind of acts like it has more mass? Because of what the definition of momentum is, mass times velocity. Now you can't actually give something more mass, because mass is how much stuff something's made out of. But if something acts like it has more mass, doesn't it take more energy to make it move? That's like an inertia thing, right? And so it's going to take an ever-increasing amount of energy to get something to go faster, 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 if you have a dilated momentum for that something. And so people say, well, why can't we get things to go faster in particle accelerators without using a lot of energy? Doesn't that kind of answer the question? Because as soon as you make an electron go faster, maybe you get an electron to go so fast that it gets fast enough that it's acting like it's a 10-kilogram bowling ball. Then you get it going even faster, and it's acting kind of like it's, I don't know, a transport truck. Aren't you requiring the particle accelerator to do more and more work, deliver more and more energy, the faster it goes, to get it to go that next little threshold faster? So you notice that when we look at particle accelerators, the particles get faster and faster and faster over the decades as we make our accelerators, more and more powerful. But the particle accelerator designers are demanding more and more energetic power sources. Maybe they want their own nuclear reactor dedicated to just that particle accelerator because they want to make things go even faster. You follow the logic on this one? So that's kind of a thing that we got to keep our eyes on. Classical momentum, P is equal to mv. But relativistic momentum, we've got this dilation factor. Now, at the speed of light, at c, the object, like we say, would have an infinite momentum. Now, following from the thinking of classical mechanics, and I know we're doing a little bit of fudging here with classical mechanics, if I have infinite momentum, then I would have to apply infinite force, right? And if I have to apply infinite force, then I would end up having to apply infinite energy, because work is equal to force times distance. And so like we do get up against a brick wall on this one. We can only get things so fast before we start to run out of energy. Now if I was going to go for the short story, these are the short story items. And they should just be like little bullets on your page. At the speed of light, or at least as we approach the speed of light, the length decreases and approaches 0. Time increases for an outside observer. And we could say eternity, but approaches infinity. We talk about the idea of limits. And momentum approaches infinity as well. And that's somehow connected to mass. All right, so if you're working on the worksheets here, you're just writing down these 1, 2, 3s. And there's space on page 20 for you, I think. Am I right, page 20? Should be something like that. 21? Oh. But really this 1, 2, 3 is just putting into words of what happens at the extreme of when the V value approaches C. Yep.
Like back to the elevator thing, like I'm just not like really sure like what it's saying. So like obviously it's staying at the same spot, like moving through it, but then for the observer, it's not actually because it's going down.
So for the observer in the elevator, we know that there's an x velocity initially, and that x velocity would still be there at the moment of impact on the floor of the elevator. But if the elevator approaches the speed of light, then by the time it hits the ground, we assume that the elevator's speed would be around the speed of light. So effectively, the y velocity of this object would be around the speed of light. But we've got a v here. But then if you have a horizontal that's nearly c and a vertical component that's nearly c, then the hypotenuse would by definition be greater than c. And so the only thing we can do to sort of like make that be okay in the universe is to stretch out space. So they would have to travel further. I know that's weird, right? Absolutely it's weird.